All right, so we are looking at page 118, second half of section 2.6, talking about velocities. Velocities. All right, we're just going to do an informal discussion here, so you don't have to worry about writing this down or anything like this. I just want to kind of talk through some common sense with you here, okay? On page 118, they tell me, in general, suppose an object moves along a straight line according to an equation of motion, S is equal to F of t, where S is the displacement. Now, displacement is a little bit different than plain distance, because it's distance in a particular direction. The book calls it directed distance. So S is the displacement of the object from the origin at time t. The function f that describes the motion is called the position function. So S equals f of t, we would just call our position function, because it's going to tell us what's the position of our object at any time t. So it's the position function of the object. So if we are talking about distance and rate and time, for us the natural formula that we learned when we were younger was distance equals rate times time, right? And you could solve that equation. If you had distance equals rate times time, you could solve that for the rate or for the time and rewrite that equation. So like if I wanted to solve it for rate, I would just divide both sides by the time, and I would get rate is equal to distance divided by time. So when we're talking about velocity, because we're looking at a distance in a particular direction, then we could think of that as our rate is going to be our velocity. Our distance is going to be our displacement divided by our time. Okay, so if I want to think about my displacement, it's basically going to be the position that I am when I stop minus the position that I am when I started, right? So basically stopping point minus starting point would tell me my displacement. So if I drew a number line up here, or a horizontal axis that could represent my position function, and I said, okay, here's my origin, and I could represent my position at any time t on that position line. So we could go through and we could say, okay, if time is equal to a, then this could represent my position when time equals a. Maybe time is 3 or time is 5 or time is 17. But that would just represent the position that I am. I go a little further down and I can let h represent the change in time. So if I start at a and I change my time by h, then that would just be start at a and add h to it. And that would be my position at time t equals a plus h. So this first little displacement right here, we could call f of a, because that's my position at time a when I plug a into my position function. And this displacement would be f of a plus h, because if I take my time a plus h and I plug it into my position function f of t, that would give me f of a plus h. So if I wanted to see the displacement, stopping point minus starting point, it would just be f of a plus h minus f of a. So that would be a way that I could represent my displacement, f of a plus h minus f of a. And then the change in my time from my stopping time to my starting time, remember we said the change in our time would just be h. And you could also see that if you did, okay, this time was a plus h and this time was a plus h minus a would also just leave me with h. So in essence, it's the same idea as if I do y2 minus y1 over x2 minus x1. It's just the rate of change of my position, my displacement, with respect to the rate of change of the time. So we say all of that to help us understand that if I wanted to find velocity, I could represent it in this way. If I wanted to find something the book calls instantaneous velocity, that means I want to know the velocity at a particular instant in time. If I want to know it at an instant in time, then I want h, my change in time, I want that to be as close to 0 as possible, right? Like almost indistinguishably away from 0. So the way that I can represent that is with a limit, right? Like I can say my instantaneous velocity would just occur as the change in my time got closer and closer and closer to 0. So I could say then that instantaneous velocity will be the limit as the change in my time approaches 0 of the equation that we just created for velocity. So in the middle of page 118, they tell me instantaneous velocity will be equal to this formula. That is the same formula that we had yesterday for slope of the tangent line. So rather than just say, turn to page 118, here's the formula they give you, whether you understand it or not, just accept it. That's what we're going to do. That's what we're going to use it for. I think this gives us a little bit of an intuitive understanding of how that formula could represent the velocity at a particular instant of time so that it's more logical to us. Okay? So we saw yesterday how that formula could represent the slope of the tangent line at a particular point. That point is kind of like an instant in time, right? And so the same thing here, we're looking at instantaneous velocity will be represented by that same equation. So here's the nice thing. Today we're going to do the exact same thing with the exact same formula that we did yesterday. We just call it something different. Yesterday we called it slope of tangent. Today we call it instantaneous velocity, but we get extra practice with the same thing. Okay? So look, if you would, at example number 4. Example number 4 says, suppose that a ball is dropped from the upper observation deck of the CN Tower 450 meters above the ground. What is the velocity of the ball after 5 seconds, and how fast is the ball traveling when it hits the ground? Now, in order to do this, we're going to need the equation of motion. And the equation of motion is S is equal to F of t is equal to 4.9 t squared. So typically we represent S as our position function, right? S equals F of t is our position function. So all we're saying is that this would represent the position of my object at any time interval t. Now, those of you that are in physics, you're very familiar with that formula already, but that is not a formula that you would be expected to know. I would give it to you on a quiz, I would give it to you on a test, and they will give it to you on the AP exam. That's not something that you would be expected to pull out of the clear blue sky. Okay? So, if that is our equation, they ask me to find the velocity after 5 seconds, and then they're going to ask me to find how fast the ball is traveling. That's velocity 2, right? So if I'm going to find velocity multiple times, we said yesterday that if they're going to ask you to calculate something several times, instead of plugging a number in the place of A, it's better to just leave A in there. And so that's what we're going to start with. We're going to find an equation for instantaneous velocity for the equation of motion. So there's that same formula that we worked with yesterday. So this says take A plus H and put it in the place of t in your function. So we're going to come right here and we're going to put A plus H in the place of t in our function. So that would be 4.9 times A plus H squared. 4.9 times A plus H squared. Then we're going to subtract from that F of A. So that means put A in the place of t in our function. So if we put A right there, that would be 4.9 A squared. Then it says divide that whole thing by h and take the limit as h approaches 0 of that function. All right, so now we have it set up. It's not well behaved, right? If I do direct substitution, get 0 in the denominator. So I'm going to do some algebraic simplification. So what you got? What you want to do? Okay. So we're going to FOIL out A plus H and then distribute the 4.9. So just simplifying here. Let's start with FOILing the A plus H. So A plus H times A plus H is going to give us A squared plus 2AH plus H squared. And if you want to go ahead and distribute your 4.9 in the same step, you don't have to write it as a separate step. I just write each individual step separately so that I don't confuse anybody. But you don't have to show as many steps as I do. So 4.9 times A squared gave us the 4.9A squared. And then 4.9 times 2AH gave us the 9.8AH. And then 4.9 times H squared gave us the 4.9H squared. and then we already had the minus 4.9a squared, so we'll bring it down as well. All right, then the 4.9a squared and the negative 4.9a squared are going to drop each other out, right? And so what I'm left with is just the 9.8ah plus 4.9h squared over h. What can I do next? Take out an h. So if I factor an h out of the numerator, then I'll be able to cancel it top and bottom, right? And then what I'm left with is 9.8a plus 4.9h. What is that? Polynomial. Polynomials are well behaved, right? Whoop whoop, direct substitution. So let's go through and just put 0 in the place of h. So if I'd use direct substitution and I put 0 in for that h right there, 4.9 times 0 would drop out, and I would just be left with 9.8a. So what we just created was a formula for instantaneous velocity for the equation of motion. So I could use that then to find the velocity at any instant. So if they said find the velocity after 5 seconds, after 7 seconds, after 8.36 seconds, after 25 seconds, all I got to do is just keep plugging into that formula fast and easy, right? Okay, so it said, what is the velocity of the ball after 5 seconds? So I want to know the instantaneous velocity. I want to know the velocity at the instant when the time is 5 seconds. So I'm going to go through and put 5 in the place of a in that formula we just created. So I can come over here and put 5 in the place of a, and I'll get 49. I do want to get in the habit of labeling my answers. On the free response section of the AP exam, each of your questions typically has like an A, B, C part or an A, B, C, D part. The whole question is worth 9 points. So you're going to do all this work for part A, for part B, for part C, for part D, trying to pick up points. You will get 1 point deducted if they tell you to label your answers and you don't label them. That would be really frustrating to do all of that work and lose a point for something simple like a label, okay? So we want to get in the habit of whether the book tells me to or not, we're going to label everything all year long, so it's just a habit for us, okay? So when I'm looking at this, remember that we said that velocity was just the displacement divided by the time, right? So all I need to do then is see what was my displacement or my directed distance being measured in, and what was my time being measured in. So they told me that I was 450 meters off of the ground, so my distance must have been in meters. And they told me that we're working for 5 seconds, so my time must be in seconds. So my label is just going to be meters divided by seconds, the distance divided by the time. All right, for B, it says how fast is the ball traveling when it hits the ground? Fantastic. I have an equation for velocity. All I got to do is stick the time in there. I don't know how long it took the ball to hit the ground. I don't know what the time is. They didn't say find the velocity of the ball when it hits the ground after 12 seconds. They didn't tell me how long it takes. I'm going to have to find that. So there's kind of a hidden question in this problem. I'm going to have to figure out how long does it take for the ball to hit the ground. To do that, I'm going to go back to my position function. Because remember, that equation tells me the position of my object at any time. I know that from the top of the tower all the way to the bottom is 450 meters. So if I dropped it off the top and I want to know how fast it was going when it hit the ground, it will have traveled through all 450 of those meters, right? So I could put 450 in for S, and that would enable me to solve for T. And that would tell me my time that it took to drop it that whole distance. That would tell me the time that had elapsed when it hit the ground. So I'm going to go through and divide both sides by 4.9 and then take the square root of both sides, and I get plus or minus 9.6. Now, although time can be, T minus 10 seconds and counting when you're launching something, we're talking about we dropped it at a time of 0 as our starting time, so we're going to go a positive 9.6 seconds here. So my time is 9.6 seconds. So now I can figure out how fast it was going when it hit the ground, because now I know how long it had been traveling, so I know what time to put into that velocity equation. So we'll put 9.6 in the place of A in that same equation that we had created, and we get 94 meters per second. So that's how fast it's traveling when it hits the ground. So we looked at this definition that we were using for slope of the tangent, and we looked at how it could be equated as an instantaneous velocity. We actually could generalize that a little bit further to give it some more applications, because this works not only for velocity, but really for any rate of change that you can write as a change in one quantity over a change in another. So if you want to find the instantaneous rate of change of one quantity with respect to another, we're going to be able to use this same formula. Because in essence, a rate of change is basically the change in your y over the change in your x. And if I want to know it at a particular instant, it's going to be at the instant when that change in x is approaching 0. So any quantity that I could think of that I could write in that way, I could use this equation for. So we could generalize this to say that slope of the tangent line is the same thing as instantaneous velocity, is really the same thing as any instantaneous rate of change that I could write that way. And in the next section, they're going to go, oh, by the way, that thing you've been doing, yeah, that's a derivative. So we'll get there. So look at example number 5. Example number 5, on the top of page 20, they talk to us there about instantaneous rate of change being interpreted as a slope, and the several different ways that we can write that as we've been doing. So example 5 says, temperature readings T in degrees Celsius were recorded every hour starting at midnight on a day in April in Whitefish, Montana. The time X is measured in hours from midnight, and the data are given in the following table. So there on page 120, you see the table of values. Now, so that you wouldn't be confused when they said 2, whether they meant 2 a.m. or 2 p.m., they're kind of going military time here. Like you'll notice at the bottom of the first column, that's 12 noon. And then the top of the next column, they're calling it 13. That's like 1 in the afternoon. 14 is 2 in the afternoon. 15 is 3 p.m. 16 is 4 p.m. Do you see how to read that? Okay. So those are the times they went through and they took temperature readings on the hour every hour for a 24-hour period. All right. So A says, find the average rate of change of the temperatures with respect to the time from noon to 3 p.m., noon to 2 p.m., and noon to 1 p.m. Okay. So if you look at that table, let's start with noon to 3 p.m. If you look at the ordered pair at noon, which was 12, the temperature was 14.3. And at 3 p.m., which is 15, the temperature is 18.2. So they asked me to find the average rate of change of the temperature with respect to the time. So we want the change in the temperature over the change in the time. I'm literally just doing slope. It's as if I'm looking at this and saying this is x1, y1, this is x2, y2. I can go through and say y2 minus y1. That gave me 18.2 minus 14.3 over x2 minus x1. 15 minus 12. So that gives me 3.9 over 3, or 1.2. So we're saying during that 3-hour window, the rate of change of the temperature, it was going up like 1.2 degrees per hour kind of thing. That's the rate of change of the temperature with respect to the time at that time of day. Okay? Then it says, find the average rate of change from noon to 2. So I could go through and do the same thing. I could say, okay, let me pull those two ordered pairs, y2 minus y1, x2 minus x1, and that gives me a rate of change of 1.5. Then I could go through and say from noon to 1, same thing, y2 minus y1, x2 minus x1 gives me a rate of change of 1.7. So I found those average rates of change. We'll come back and talk about what they mean to us in just a second. All right, then B says, estimate the instantaneous rate of change at noon. I want to know at 12 o'clock noon, what was the instantaneous rate of change of the temperature? I don't know. They didn't take that information. They only took the temperature once an hour. How am I supposed to know what it was doing at the minuscule portion of a second at 12 o'clock noon? I mean, they didn't even take readings every minute, let alone every part of a second. How am I supposed to calculate that? Well, here's how. Knowing that instantaneous rate of change, instantaneous velocity, and slope of the tangent line are all the same thing, here's how that can help me. Because if I don't have the information that I need to find the instantaneous rate of change, like I don't here, I can use the slope of the tangent line to find it instead. So I'm going to take all those ordered pairs on page 120 and I'm going to plot them. Okay, so we came over and we plotted those points and then we played dot to dot, and that's where we got the graph that you see here. That literally is just a graph of those temperatures on page 120. That's the graph that you see on page 121. I want to know the instantaneous rate of change at 12 o'clock noon. I want to know the instantaneous rate of change right there. Okay, find the slope of the tangent line right there and it'll be the same thing. So what I'm going to do is I'm going to hand draw a tangent line so that it is tangent to the graph at that one point. That is my one point of tangency, 12 right there. Okay? So if that's my point of tangency, now this is not going to be perfect. Anytime I hand draw anything, it's not going to be perfect, right? But I'm going to do my best to draw a line that only touches my graph in one spot, and the one spot where it touches it is at 12 o'clock noon. Okay? So we've got a line drawn there. And then I'm just going to find the slope of that line. So if you were going to find the slope of that line, you could pick any 2 points that you want off of the slope of that line. Okay? So I just chose A and B. And to me, when I looked at A, it looked kind of like it was about halfway between 8 and 9, so I called that 8.5, and then it looked right on that Y value of 8, so I called that 8.58. Now, your line, when you looked at it, you might have thought that was 8.78. That's okay. It's an approximation. Yours might be a little bit different than mine. That's perfectly fine. Then point B up here, when I looked at that, that looked to me like it's going... it's right on the 14, but it's going a little bit past the 18, like a little above it, so I called that 18.3. You might have called it 18.1. We're going to get approximately the same thing. It's okay. So I'm going to use those 2 points to find the slope of my tangent line, right? y2 minus y1 over x2 minus x1, just our normal slope formula. And so the slope of my tangent line at 12 noon was 1.9. If that's the slope of my tangent line, that's also my instantaneous rate of change. So I just found the instantaneous rate of change of the temperature. It's changing at a rate of 1.9 degrees Celsius per hour. So at 12 noon, that's its rate of change. Now, to try to help us understand that really might be the correct answer, or to help us catch ourselves if maybe we had made a mistake somewhere and gotten an answer that was totally off, average rate of change can help me with that. Back here, when we were doing these average rates of change, in essence, what we were doing was, it's like when we make a table of values when we're finding the limit. Okay, my goal here is to find the limit as the change in time approaches 0, right? So if I were approaching 12 o'clock noon, I would use values, like if I were approaching from the right, I would use values off of the only values that I had off of my table. I would use 3 and then 2 and then 1 as I were approaching it. So if I were making a table of values on my own, I probably would have calculated and gotten 1.2 and then 1.5 and 1.7. Basically, those are just successive approximations that are getting closer and closer to that change in x being 0. Here is change in x was 3, here's change in x is 2, here's change in x was 1, and then that was as close as I could get. Yeah, I'd really rather be plugging in 0.1, 0.0, 1.001, but I didn't have that data, so I couldn't use it. The nice thing is, though, that this kind of gives me an idea of where this is going. So when I get an answer of 1.9 down here, I can go, yeah, that looks legitimate. That makes sense. Whereas if I got an answer down here of -3, something's wrong, right? This was not leading me towards -3. That doesn't look like it could be a plausible solution. The other thing that those things were doing for me, remember when we started our definition of slope of the tangent line? The other way that we could think of this is when they gave me those 2 points, like noon and 3 o'clock, and I went through and calculated the slope. That's the same thing we were doing when we were drawing the secant line, and we were saying, okay, let's find the slope of the secant line as an approximation of the slope of the tangent line. That's the same thing. We went through and we found that slope 1.2, that would be the slope of that secant line right there, and you can see that gives me a good way of approximating the slope of my tangent line. But as we saw yesterday, the closer those 2 points get together, the better the approximation is. So then when we went from noon to 2, that would be like if my 2 points that I used for my secant line were here and here. That's going to give me a better approximation. That green line, that green secant line, is closer to my actual tangent line. And then we did one more. We used the noon to 1 o'clock. So that would be using my point at noon and using my point at 1 o'clock. And you can see that there with the blue line, that's going to be my best approximation yet. So again, trying to help us understand how instantaneous velocity, instantaneous rate of change, and slope of a tangent line at a particular point can all be the same thing, and how we can use them to help us find other quantities. All right, so here is our homework for tonight on pages 122 to 123. Number 13 was your challenge last night, so if you've already done it, I've already got you checked off, so I know that. You don't need to redo it, but if you didn't do it last night, be sure you do that as part of your assignment tonight.